Welcome everybody. In this video, we're going to talk about damped vibration systems. So dampening is what happens when you introduce some resistive force, something that's resisting the motion of the object on the spring. And so things like wind resistance do this. So when you're moving through the air, the faster you move, the more the wind hits you and slows you down in parts of force. And so in that way, so what's happening is that the force is proportional to the velocity. So we're going to introduce a term into our differential equation to do just that. All right. Before we do that, I just want to review what we were looking at last time. Okay. So last time, we were looking at the differential equation that just described the motion of an object on a spring, perhaps subject to some external force, okay? And we were looking at what was going on here. So the picture would be something like this. We have a spring dangling from the ceiling, or maybe it's laid out horizontally, it doesn't really matter. And it's wiggling up and down, right? And the object has some mass, m, that's what's denoted here. The spring has a spring constant, k, that's what's denoted here. That's how hard the spring pulls back when you pull on it. And we may have some external force given by some trig function. So you might imagine that we're shaking this platform up here, up and down. Oops, bumped my camera. Shaking the camera. Shaking the ceiling up and down as the object's wiggling, right? And so that introduces a whole other force to the system, okay? So what did we see here when we did this? Well, we saw there were actually two cases. When you solve this differential equation, what are you going to do? Well, what we did is we divided through by m, all right? When we divide through by m, we get y double prime plus k over m, but that was the same thing as omega naught squared. That's what we defined omega naught to be, root k over m. And then f divided by m, I'm just going to call that a. All right? So we get this. Now, this omega naught is an important thing. This is the natural frequency of the spring, right? So if there was no force, that would govern the frequency at which this thing oscillates. And so I think we can set this up in this demo I have here. Let me, oh my goodness, I almost closed it. Let me, just set the force on the right-hand side to be 0, and we see that we get a just a very regular oscillatory behavior. As time goes on, you can see the object on the left-hand side, that purple ball, is just the object on the spring. And as I let time go on, it bounces up and down, right? As we would expect to occur. Now, if I introduce an external force, right? If I make that coefficient A non-zero, so we have some external force. Okay, and I have a sign up here. On the paper I wrote a cosine. It's the same idea. But you see what happens here when I introduce an external force, the picture looks a little bit different, right? We don't only have the oscillatory behavior up and down, but we also have the whole system's kind of moving up and down. Like the center point of the oscillations is moving up and down. And you can kind of see that in the curves that I've drawn here. The green curve that's essentially the particular solution to this differential equation. And I think that's purple. The purple curve, actually the blue curve back here in the background is the complementary solution to the differential equation. That's the one that's given by omega naught. And when you put those together, you get the purple curve, which is kind of following both of those, right? Now, there's two things that happen here. There's two situations that could happen, and that has to do with the relationship between omega and omega naught. All right. If omega is not equal to omega naught, then we're seeing basically what we saw in the picture. So we get this oscillatory behavior. Now, if omega equals omega naught, what happens? Well, now the force has the same frequency of the natural vibration of the spring system. What's going to happen there? Well, this is what's called resonance. So let's take a look at that. What I'm going to do is I'm going to change omega on the slider, and you can see as I change omega, the green particular solution is lining up, right? The frequency corresponding to omega is lining up with the frequency, the natural frequency of the spring. And you can see that things are getting kind of crazy here. The amplitude is starting to get pretty high, and it's starting to get very high here. And if I actually align them so they're equal, that's what we're calling resonance. Now, it's not just very big, it's growing and growing forever, right? It just keeps on going until in real life the spring would just break. Something would go terribly wrong here, right? So why is this happening? Well, you know that when you solve this differential equation and these parameters, these two parameters here are equal, the solution, to find the particular solution, you have to introduce a parameter t, right? So the particular solution in this case ends up having a t times, right? But you have this multiple t. That t is what's doing this. This is a line, right? The amplitude is growing linearly. Well, this is a linear factor, right? And actually, and it's going to be some multiple of t. So the slope of that line is given by a and b, right? So that's the situation that we were looking at last time. So this time what we want to do is we want to look at the situation where we introduce this resisting force, okay? So what we're going to do is we're going to throw into our system a new force that's proportional to the velocity. The velocity is given by y prime, all right? And so I'm going to have some multiple of y prime in here. And so something like this, okay? So this is going to be the differential equation used for a damped system, okay? And so what you can imagine is going on here is that we have the spring holding the mass, but then there's resistance. So oftentimes they describe this in terms of a dash pot. A dash pot is when you attach some platform to the object and you submerge it in some kind of viscous fluid. So as this object is moving up and down, if I set this into motion, the fluid is going to cause a resistance to the motion, kind of like wind resistance. And so let's think about what might happen if we do just that. What's going to happen if I have this resistance? Well, you might expect the object to begin oscillating up and down, but then as time goes on, of course, that resistance is going to weigh on the system, and that slowly over time this should oscillate less and less and less until it kind of settles down, right? And so that is exactly what happens, okay? And there are three situations for this. When you solve this differential equation, what are you going to do? You're going to look at the characteristic polynomial, okay? So you're going to maybe divide through by m, all right? Now, when I divided through by m, I changed this c to a gamma. I could have written c over m, but instead I'm writing 2 gamma. So what I'm thinking of is gamma is the same as, 2 gamma is the same as just c over m. You'll see why I want to do this, because it's nicer to write things in terms of gamma than in terms of c over m. Okay, so when you divide through by m, you get this, and gamma is just, think of it like this. You could just replace gamma with c over 2m, same thing, right? Now, when you solve this differential equation, what do? You look at the characteristic polynomial. Right? The characteristic polynomial is this. And what we do is we find the solutions. Now, the solutions are given by the quadratic formula, right? So, okay, so what we get is we get this, okay? And let's simplify it a little bit. We get gamma, negative gamma, plus or minus, well, that 4 comes out, cancels with the 2. We just end up with gamma squared minus omega naught squared. Okay? Now, there are 3 situations that can happen here. Okay? This thing under the radical, that's called the discriminant, that thing could be negative. All right? So if, in other words, if gamma is less than omega naught, then what we have is we have a system that is underdamped. We call this underdamped. What does the complementary solution look like in this case? Well, when gamma is less than omega naught, this is a complex number, so an I comes out. When we get an I, we get sines and cosines in our answer, right? So our complementary solution is something like this. And I didn't quite leave myself room here. E to the minus gamma t needs to be included as well. That's an e to the minus gamma t. Okay, and the reason that needs to be included is because we have this real piece over here. And you know when you get a real part, that comes out as a factor of e to the minus gamma t. Right? Now, by the way, sometimes they will just say this. This is the same as saying c is less than the square root of 4mk. That's the same thing as saying gamma is less than omega naught. And just use this relationship here. Okay? So that's the underdamped case. Okay? Now, what else could happen? Well, gamma could equal omega naught. If gamma equals omega naught, we call that the critically damped case. This is critically damped. When it's critically damped, what is the complementary solution that we get? Well, that means this term is 0, so our solution is just minus gamma, but that's a repeated root. And when you get a repeated root, we know that we have to introduce a C1 plus C2t times e to the minus gamma t. So we get a solution that looks like this. Notice there's no trig functions here, right? And that's the same thing, by the way, as saying this. Okay? Now, finally, what's the last thing that could happen? Gamma could be greater than omega naught, and that's what we call the overdamped case. This is called overdamped. What does the complementary solution look like? Well, in this case, that means that this thing under the radical is positive, and so we get a real number, and so we have 2 distinct real roots. Both of them, if you look at this, you can see that they're both going to be negative. Okay? So you're going to have, these are our 2 roots, R1 and R2, where R1 and R2 are both negative. It's not too hard to see that they're negative by looking at this. Okay? And by the way, this is the same, of course, as saying that C is greater than root 4mk. Okay? Those are the 3 situations. Now let's go take a look at these. Let's take a picture, look at some graphical descriptions of what's going on here. Now notice in these examples, it's using an x instead of a y. Just think of x and y are x is replacing y here, all right? I didn't want to change all these x's to y. It was going to be too much work. And also, instead of primes, they have dots. This is a convention in physics where whenever they take derivatives with respect to time, well, not whenever, but a lot of times when they take derivatives with respect to time, they use dots instead of primes, just to emphasize the idea that, hey, this is with respect to time, not some other variable. Okay, so, but this is the same as just y double prime. This is the same as just y prime, and this is the same as just y. Okay, so x is y here. And we can see here that when gamma is less than omega naught, we have the oscillatory behavior. And you can see as this thing, watch that purple ball on the left, it just kind of peters out. It wiggles a little bit, but then it just dies out, as we would expect, right? Now, what happens when I let gamma approach omega naught? Well, that's when we're approaching that critically damped case. Well, look at this. It's oscillating less and less. Can't really oscillate. There's too much resistance. And when we once we get to critically damped, once gamma equals omega naught, there is no oscillatory behavior. It's all gone, right? And when we go past omega naught, it's completely gone. That's the overdamped case. Okay, so that's the situation. These are the situations that we're talking about here. All right. Now, the last thing that we need to discuss is what happens with this forcing term here. Okay. Well, actually, before I go there, let me point out this is kind of part of that. So when we write down our solution, right, our final solution is going to be, we know that it's going to be the complementary solution to the complementary equation, plus the solution to the particular, plus the particular solution. It's the solution of the complementary equation plus the particular solution, and that's going to be our general solution, right? The complementary solution, the solution to the complementary equation, this is called the transient component of the solution. The transient component. The particular solution is called the steady state component. Okay, so we have just talked about the transient component. This is the component that dies out over time, because in every single case, it's got an exponential function with a negative exponent. So these all decay as time goes on. So the transient component is the component that just kind of dies off. Now, if you have some external force that keeps influencing the system, well, that's just going to stay there, right? That's just going on and on. It's doing whatever it's doing. And that contributes to the steady state component of the system. And so what we're going to talk about next is the steady state component. Now, I'm not going to go through the steps to find this. We've talked about this in previous videos, so this is a good exercise for you. You can find the steady state component. And what you'll see is that it looks like this. We can write it in this form. And as I said, in a previous video, we talked about how to put the solutions into this form where they're just written in terms of a single trig function in terms of some phase shift parameter here. Okay, so when you write out the steady state solution, you get this coefficient on the outside, right? This has to do with the amplitude of the solution, right? The question is, how does this amplitude behave? Okay, so let's take a look at an example. So I've set this thing up with the forcing term on the right-hand side. All right. Now notice that I'm going to change the frequency of the forcing term. Okay, so what we're seeing here is we're seeing an object. I've set in initial parameters here. I've got the initial position set at 1, the initial velocity set at 0. I got some mass, the dampening constant, the spring constant. I got some parameters set here. And what I'm doing is I'm looking at a force term on the right-hand side with some frequency omega, right? Now I'm going to change that frequency. So I'm going to change that frequency. We're going to see what happens. Notice that when the frequency is very small, you can see at the beginning we have the frequency governed by the spring system, all right? But that starts to decay over time. That's the transient solution. That starts to decay away. What takes over in the long term is the steady state solution, right? And that's governed by the omega, okay? So omega is what things kind of end up going to. Let me continue to play around with this omega term here. If we look at this, look at this. Did you see that? As I increased omega, let me back it up again. So it looks like it's just kind of like, you know, just kind of going to this steady state solution, going to the steady state solution. But something interesting happens here. We get a pulse. Notice that when omega is right around here, that's a notable point, right? The amplitudes are quite large here. What's going on? Why is this happening? And how do I find this omega that's making that happen? When I go past that, then look what happens. Things kind of just fizzle out like this. Now there is an underlying steady state solution here. It's not going to zero, right? This is really the steady state solution governed by the forcing term. Now it's subject to that resistive force, but it is there and it's not going away, right? But it's interesting that for certain frequencies we get this kind of large amplitude here. So how does that come to be? That's what we want to explore next. Okay, so and it all comes from this term. So this term is governing the amplitude of the solution here. Now, what's making this big? Well, the top is just a constant. It'll be big when the bottom gets small, right? When you divide by a small number, you get a big number. So we're looking to see where this thing is smallest. So we want to minimize this function under the radical down here. Okay? So to find, what we want to do is we want to find that frequency called W max that maximizes the amplitude. Okay, so what we're going to do is we're going to minimize this function. Oops. Minimize Okay, so I cut the video here because I started to work through this and then I realized, you know what, I think this is a really good exercise for you, okay? So I'm going to leave this as an exercise. I'm not going to do the steps here. And you can read about it in our book. But let me just point out there are two cases, okay? There are two situations that you have to pay attention to. There is the case where C is greater than or equal to 2mk, and there's the case where C is less than root 2mk. And you can see that if you just graph this function, okay? So if you go and look at the graph of this, what we're looking at here is the situation where C is less than root 2mk. And what you can see is that it has a minimum right over here. And so by minimizing that function, just using Calc 1 techniques, you can find that minimum. And you can find the value of the amplitude that would correspond to that minimum. Okay. Now, and that's the maximal amplitude, because remember, we're minimizing the denominator to maximize the function as a whole. Now, if C is greater than 2mk, if I make C bigger, you'll see that that's the other case. We don't have some positive value of omega that minimizes the function. The function is just minimized at omega equals 0. Okay, so I just gave you the answer for the greater than or equal to root 2mk case. But for the less than root 2mk case, we see that there is a positive omega that you can find that will maximize the amplitude. And that is exactly what is happening here. When omega hits that value, that's what's making this big pulse occur, where we have these quite, oh wait, this is the wrong, that's the wrong guy. I'm supposed to be moving this slider. That's where this big, you know, that pulse right there happens, right? And I've computed it in this particular case. You can see it's written down here. I actually found omega max, right? And that's the value that when this gets close to that, that's when this big pulse is happening. And I've got it right about there. See? Okay, so that's it for this video. I know I didn't go through too many details, but I think that's because we've already talked about how to do that stuff, and I don't want to bog the interesting discussion down with the details. So hope you learned something in this video. I'll catch you next time.